Hello everyone, and in this video we have another radians and sectors and segments exam question. This one's occurring a little bit later through a paper and is worth 8 marks. So this is a trickier question than very often you get. So a rather intriguing looking shape there. So it says we've got circle C1 has the equation x squared add y squared is 100, so it's centered on the origin. And we have circle C2 has the equation x minus 15 squared add y squared equals 40. So I think the first thing to observe is that this point here, which could be useful to us, has the coordinates 15, 0. So the center of C2 is at 15, 0. Something else that I think is going to be quite useful to us is to draw a couple of little triangles like this. Okay, these are going to be useful to us in the calculation of our angles, because we're going to need to know, I'm going to call this angle here alpha, and I'm going to call this angle here beta. Okay, so we're going to need to work out alpha and beta. Now, first of all, we've got to, it says, show that the angle AOB is equal to 0.635 radians to 3 significant figures. So in other words, we've got to first of all find out this whole angle here, which would be, in my case, 2 alpha. In order to do this, one of the first things we need to do is we need to work out the points of intersection of the two circles. So we could do with knowing certainly what the x coordinate is for sure, and possibly the y coordinate of these 2 points of intersection here. And in order to do that, we're going to solve the two equations simultaneously. So let's have a look at what we've got. We have got one equation is x squared add y squared is equal to 100. And our other equation is x minus 15 all squared plus y squared is equal to 40. So we've got to solve these simultaneously. And actually, why don't we just, let's make this one, call that equation 1, that one equation 2, from 1. So from equation 1, I'm just going to rearrange it to make y squared the subject. So y squared is equal to 100 minus x squared. And then we're going to sub equation, I'll call that 3, sub 3 into 2. So we're now going to sub this equation into this equation. So we've got x minus 15 all squared plus our y squared, which is 100 minus x squared, is equal to 40, like so. Okay, so x minus 15 squared, and there we go. We found out that y squared is 100 minus x squared. So now we can expand this bracket. So we get x squared minus 30x plus 225 plus 100 minus x squared equals 40. And let's collect, oh, that's nice. The x squareds cancel. That's super helpful. And now we can basically, and we've got 30x here, which we could just take over the other side. So that is 30x. I'll just pop that over onto the right-hand side. And then we've got 225 plus 100 minus 40 is going to give us 285. So 285. So our x is 285 divided by 30. Divide that by 30, and that gives us 9.5. Okay, x is equal to 9.5. Now that is going to be super useful to us. So we've just solved the two equations simultaneously in order to find a value for x. I'll find y if I need to in a minute. We may not need it. So we have found that this distance here is 9.5, okay, because we've basically just found that the x coordinate of A is 9.5. We don't yet know what the y is, we'll leave that blank. And the x coordinate of the B is also 9.5. And again, we don't know the y because there's a straight line coming down between these two here. So the reason that this is useful is because notice that the center here is at 15, okay, and this is 9.5. So this means that this must be 5.5, the distance from there to there. That's going to be useful to us as well. So let's pop that in, 5.5. And we've deduced that again because this whole length from here to here is 15, and this bit is 9.5. Perfect. So how does that help? Well, we also know that the equation of C1 is x squared add y squared is 100. In other words, its radius is 10. And likewise for C2, its radius is root 40. And that's going to be very useful as well. So root 40. I think, we've got enough information now to start to crack this. So let's have a work, first of all, see where we're going to go from here now to calculate our angle alpha. In this little right angle triangle, if I call that point there X, so let's just have a bigger sketch of this triangle so we can see what we're dealing with. There's our alpha, that's the origin. That's A, I'm calling that point X, that's a 90-degree angle. This is 10, and that's 9.5. So we can use regular trig now to find the angle alpha. So we're going to say that cos of alpha is equal to adjacent over hypotenuse. So we're going to do inverse cos of, make sure that we're in radians. Oh, that's an important point, actually, which I haven't emphasized enough. This topic and those formulae that we've been using, the half r squared theta and the L equals r theta, they basically only work in radians. So that's a super important point. We must be in radians. So make sure our calculator is on radians, and we're going to do inverse cos of 9.5 divided by 10. And that gives us 0. Let's write down alpha is therefore equal to cos to the minus 1 of 9.5 over 10. And that alpha is therefore equal to 0.31756. Okay, now the angle in question, angle AOB, so the angle AOB is 2 times my alpha. So that is going to be 2 times 0.3756. So let's times that by 2. Gives us, rather fortunately, 0.63512. And we're after this correct to 3 significant figures, which is 0.635 to 3 significant figures. Now, I would emphasize here that because they've asked this for 3 significant figures, believe it or not, if you don't write that to 3 significant figures, you're going to lose an accuracy mark. So that'd be such a shame to have done all that correct working and then lose a mark there. As an examiner, it's really sad when you see a student doing everything correct and getting the correct answer, but because they've ignored that instruction to have the right degree of accuracy, you lose a mark if you don't pay attention to that. So be careful with that one. That's our part A done then for 4 marks. Now, part B. The region shaded in figure 3 is bound by C1 and C2. Find the perimeter of the shaded region, giving your answer to 1 decimal place. And this is worth another 4 marks. So what we're after here, I know that sometimes people might struggle to visualize the region in question. The region in question is we're after this perimeter. So all the way around here and round here like this. So this is what we're after. That bit that I've just gone over in bold. Now that's fine. In order to do that, we can certainly find, because these are essentially our 2 big arc lengths. Okay, there's 1 major arc there. So that is an arc length. So all we need, let's turn our attention to that one first. So we've got this angle round here. Now this angle round here is going to be 2 pi radians, a full circle, minus our 0.63512. Now notice that I've gone back, I've reverted to the more accurate form. So I think it's really important, just as a general rule of thumb, to always work to a higher degree of accuracy in your calculation than you state your final answer to. Okay, so make sure you work to a higher degree of accuracy in your calculations than what you state your final answer as. So if we go now 2 pi minus the answer, that gives us that angle in question is 5.64806. So that's the angle round there. So therefore, the arc length from C1 is going to be L equals r theta. Our radius, remember, is 10. And our theta is 5.64806. So therefore, that large arc length is going to be 56.4806. So that's our first big arc length round there. So in order to now find this arc length, we're going to need to know this angle here, angle, oh, I haven't called that anything. Let's call that y. Angle AYB there, we need to know that angle. Well, in order to do that, that's going to be 2 lots of beta. So let's have a look. There's another triangle here that we can use. So if I just draw a larger sketch of this triangle here. So this is, here it is. This is just this triangle, but enlarged. And what do we know? We know that the hypotenuse is √40. We know that the adjacent is 5.5, and that's our angle beta. So once again, we're going to say that beta is equal to inverse cos of adjacent over hypotenuse, 5.5 over √40. So inverse cos of adjacent over hypotenuse. So inverse cos of adjacent 5.5 over the hypotenuse, which is √40. Okay, that gives us that beta is equal to 0.51635. So therefore our angle, which is going to be called angle AYB, is equal to 2 times beta, which is going to be times by 2, 1.0327. So we now know this angle AYB. So we're now in a position to find the arc length here. It's going to be r times theta. So I'll call that C2, and we've got the length there is r theta. Our radius in this case is √40, and our theta we've just discovered is 1.0327. So from that we can find an expression for our length. Now let's have a look at that. So that's going to be that times by √40. There we go, is 6.5314. So therefore our perimeter is just equal to the length, the circumference of C1 plus the circumference of C2, and that is going to be that we found the perimeter of the first one to be 56.4806, and we've just found this one to be 6.5314. So we add these together, and that's going to be the answer to our question, 56.4806 gives us a total of, let's have a look and see what we're getting there. So we have got √40 times that. Now actually I'm realizing, let's think, I've made a crucial error here. Just being careful, I've realized that we have got this angle here, beta, and I've just done r times, so that angle there, 1.03, is this angle in here, which is good. And here, look, I've used that wrong angle. So I've realized that what I should be doing there is I should have done 2 pi minus that angle. So slight error there, but that's okay. We can correct that. So here we go. What we should have done here is we should say, because we found that this angle here is our 1.0327, okay? So actually, we don't want that one. We want this one round here, round the outside. So actually, it should be 2 pi minus that 1.0327. Now that's better. So let's do that then. So here we go. So 2 pi minus the 1.0327. It's looking better. That gives us, I'm going to times that by √40, times by √40. Okay, that's giving us 33. That seems a bit better. 2.0698. Let's add that together. 33 here now. 0.20698. Okay, let's add that now to our previous angle, previous length rather, 56.4806. And that gives us 89.68. So our perimeter is equal to 89.68. The question asks us to give it to 1 decimal place. So our perimeter is 89.7 to 1 decimal place, which is our correct final answer. So yes, we found, let's have a look and see what we did. We found our angle that I call beta. We doubled it there. That was our 1.0327. And then we needed to do because this is the angle that we need when we're doing our L is equal to r theta calculation. So we need to do a full circle 2 pi, take away that 1.0327. So we do 40 times by 2 pi, take away that, and that gives us the correct answer for that arc length. We add them together, and that gives us our full perimeter. So that was a slightly trickier question on the sectors and segments when this question occurs a little bit later in the paper, and that was worth 8 marks. So I would argue that that was a slightly, definitely a harder example of this type of question. I hope that you found that useful, and I will see you in the next video.